if this is slit, I'll directly give, okay, this is a source at this particular point P. So this instead of this D, no, D I'll give 0.4 meter and capital D I'll say 1 meter. Then will you use the above formulas? No, you should not use here. That at this particular point. So path traced by this ray. Before slits, both will cover same path. After slits, you see that one. So take help of the geometry and calculate. So this distance I'll give it. Then what is the path covered by the ray 2? What is the path covered by the ray 1? So calculate S1P, calculate S2P. Then what is the path difference? The path difference should be equal to S2P minus S1P. You should not use above formula. Any reason for that? D is not very much less. If D were of order millimeter, then okay. So D is 0.4 meter, not negligible. You should not use any of those formulas. If you want to calculate the intensity at any point, you should calculate this path difference. Then afterwards, what you should do, come for this formula, 2 pi lambda delta x. And this will be, then the resultant intensity will be the intensity at this particular point. So let intensity of slit, let it be I naught only. Since here the D is 0.4 meter, no, definitely this intensity will be less. So in that case, what you should do, I'll give power of a source, P naught. So what is the intensity of light reaching at this particular point at S1? Or directly, what is the intensity of light available? Since all the light will not be transmitted, only a part of it, no? So it's usually practice is like so we just say like a power of the, also like let it be P naught only. We'll calculate intensity directly at point P due to this source. Similarly, the intensity at this particular. So how do, first what we should do? First, this particular point will act like a power, no? Again, what is the power here? How you find out? You should know the area of slit here. So this is the width of the slit if you know it. This one. So what is the intensity at this point? I1 will be P naught by 4 pi SS1. Of course, intensity of both will be same, but the width of the slit will determine what is the power. Intensity into area. Now this, what is the intensity at point P? Due to first slit, it should be P1 by 4 pi S1P whole square. What is IP2? IP2 should be equal to, same thing again. I think I1 equal to, let me write here also separately. So then what is the power flowing through this? Intensity at the slit, I2 into area of the width of the slit. Okay, you'll get the power P2. Then afterwards, what is IP2? IP2 should be equal to P2 by 4 pi S2 P square. P is the power of the light at the slit. It depends upon the width of the slit here. After getting this, then the resultant intensity at point P is given by IP1 plus IP2, 2IP1, IP2 cos phi. Are you getting now? So you know, because now we know enough of ideas. Huh? So the width of slit matters as it matters. Huh? So what is A, or I'll put it this as like a, we need area only. So here slit, one slit, this will be area A1. The other slit may be little bit broader. When this discussion will come, when the distance D, what will happen? When the distance between the slits, if it is comparable to distance between the slit and screen, then the entire discussion will go off like this. It's of practically in some applications, but most of the time we don't use it. Huh? So possibility of in advanced, no, in general passage, he may dump things off like this. Huh? So what is P1? What we should call power of slit S1. So what is P2? Power of so if the source is No, here so the source is having wavelength lambda. What about number of maxima? The number of maxima again depends on d lambda only. But sir, this formula is derived somewhere like this. Still this is applicable. So this will be the number of maximas. How many maximum minimas, what we can notice, it depends upon this formula. So just do be aware of conditions of anything. So this S2P, S2, you are not going to use any of this mathematics, what we brought it. These mathematics, you are not going to apply it. Because this is applicable only when D very much less than capital D. Fine. Okay, let's take the next condition. Now slowly, I think we'll analyze. Now, if I increase the width of the slit, what conditions will come? So shall we put like this one, a broad thing, intensity is directly proportional to width of slit. So if you double the width of slit, what will happen to intensity will get doubled. Then what will happen to amplitude? And intensity is directly proportional to what? Square of amplitude. Okay, now if you double the slit, intensity will get doubled. What will happen to amplitude? Amplitude will not get doubled, am I right? So when you are doing any numericals, you keep this in mind. Huh? So when you vary the width of the slit, so what will happen to the maximas, minimas, intensity of maximum minimas, what will happen to number of maximum minima, and what will happen to the pattern? Let's analyze these conditions. Theoretical questions can be asked, any theoretical question. So I'll keep this data here. Let's see that one. If I vary the width of slit, we'll just double one of the slit. We'll see what conditions come. Initially, so we have S1 and S2. So a monochromatic ray of light is incident. Again, the condition is same. D very much less than D. Now I'm going to increase the width of the slit. You can see in the diagram, the width of upper slit is increased. Yeah, let me say it's a doubled. Line is not there. No. So there's a monochromatic ray of light is incident, lambda. Here width of slit W1, W2, and W1 equal to W2 equal to W. Let's take that one. So here how much width of slit? No, W1 dash is 2W. W2 is W only. Now what changes we should bring it here? Intensity earlier, what was intensity? Intensity was I naught. What was intensity? I naught and I naught. Now how much it will become? Doubled. So the intensity here will become 2 I naught. This will become I naught. Okay, I had to show it. Yeah. What will happen to the intensity of central maxima? So earlier it was 4 I naught, 0, 4 I naught, 0. Let me show only those things. This one. So what is the intensity of central maximum it will become? So then you have to use formula I max will be equal to root of I1 plus root of I2 whole square. So this is how much it has become 2 I naught. So this will become root of I1 plus I2 whole square. It will be 3 I naught. So the intensity is how much here now? 3 I naught. So what about the I minimum? So root 2 I naught. So I naught will come outside. So root 2 minus 1 whole square into I naught. Oh, I think this is it correct? No, it should be like this. Huh? We can't. It should be like this. Huh? Root 2 minus 1. So this will be. Look at I minimum. Will it be 0? Here you don't get complete dark. So what happened to the look at this value root 2 1.4 1.4 this one. So what will happen to brighter bands will become more brighter and darker bands will become less darker. So when you increase width of the slit, the brighter bands will become more brighter and the darker bands will become less darker. Less darker means earlier it was zero intensity, now it will be non-zero intensity. Okay, fine. So this is the when you increase the width of slit, anything will happen to pattern. I'll place it below down. Yeah. Anything will happen to pattern. Since we know some diffraction, no? So let's analyze here. Anything will happen to number of maximas. Go back to the diffraction. As you vary the width of the slit, as you vary the width of the slit. So what will happen to central secondary maxima minima? As you increase the width of slit, secondary maximum minimum may get eliminated, no? So there's a possibility here. So what is this interference pattern? It is like a overlap of two diffraction patterns. So as you increase the width of the slit, then there's a possibility of, there's a possibility of what happened? Number of maximas or minimas will decrease. Number of maximas, minimas will decrease. And anything will happen to the width of central maxima minima. You have to answer this keeping diffraction in the mind. Anybody? So any conclusion can we make it? So shall we say that, so as you increase the width of the slit, less diffraction will occur. As you increase width of the slit, less diffraction will occur. So due to, and the overlapping will decrease. So therefore, and what will happen, the fringes will become narrow. Means the width of the fringe what will happen will decrease here. And the number will be less. So I'll keeping diffraction in mind, what I say that as width of slits is increased, first point, less diffraction occurs. Okay, this one. Then fringes are narrow and number of fringes decreases. This is actually the impact of the width of the slit. Without diffraction, we had some other idea. Only intensity we talked here. How to calculate that intensity? Okay, now we know formula. And then what shall I put another thing? Intensity of maxima and minima. Now in advance, E will stress you. It's not like something diffraction not there out of syllabus. E will stress you. In diffraction or less bending of ray of light will occur instead of using word diffraction. Fringes will become narrow, number of fringes decreases, intensity of maxima and minima varies here. And this is about the impact of this particular thing. And then, so if it is if you see this one, what about the central maxima? All the fringes will happen. So as we increase width of the slit, the fringes will become narrow. I think this is what we discussed here, no? So, and as you decrease the slit, then width of the fringes will increase. Fine. So there's about one small data which is missing in books. I just wanted to highlight it. I highlighted it. Let's go for the next part. Okay, if we bring slab, then what conditions are to be followed? I think you have plenty of questions on this slab idea. Plenty of questions, not one. I think the whole theory just revolves numericals, maximum numericals are revolving around the slab only.